Hello, hello. Am I audible? Hello, am I audible? Okay, so let's begin. Um, Hope whoever can could not join today's session. Hope this recorded video that I will upload in YouTube will be helpful for you to solve your week 4 assignments problem. So yeah. So good evening, everyone. Welcome to the week 4 of doubt and problem solving session in the course of carbon materials and manufacturing. And myself, Saurabh Soni. And today we'll be discussing mainly whatever we have covered in our week 4. So I hope that you guys have watched the lecture before solving an assignment. So if you have not watched, then please watch the all the video lectures, then only it would be helpful for you to solving an assignment, and it will be a more easier for you guys. Okay, so let's begin. So yeah, the first question that I would like to interact or introduce is the HOPG. So I hope that you guys have heard this name HOPG. So let me take the pen. HOPG. So, can anybody answer that? What is this HOPG? Anyone? Okay, so I will tell you. So, this question is asking mainly about just a second. Let me. Hello. Yeah. Yes. So yeah, I was asking that what is HOPG? So this question is mainly asking HOPG is different from pyrographite because it offers a lower X-ray transparency. It has highly aligned crystals. It has a lower purity. It is prepared by heat treatment of polymers, while pyrographites are obtained from gaseous hydrocarbons. Okay, so can anybody guess that which of this answer will be the suitable as per the question? It is asking that HOPG is different from pyrographite because of what? There is two term. One is pyrographite. Okay, one is your pyrographite, and another is one is your HOPG. So HOPG and pyrographite. So this is two term. So first one question that I asked that can anybody explain the full form of HOPG? Um, Basically, here you can see the HOPG is what? Highly oriented pyrolytic graphite. HOPG is what? Highly, sorry, highly oriented pyrolytic graphite is nothing but what? HOPG. highly oriented pyrolytic graphite and pyrographite. Okay, so it is different because of what? So in this slide we will see that what is the answer and why it is different, you will see. So here as you can see, graphite uh, from graphite from pyrolysis of gaseous hydrocarbon. So here we are making a graphite from pyrolysis. So, okay, so there is a term called gaseous hydrocarbon. Okay, so you should know that what is gaseous hydrocarbon. Okay, so what is gaseous hydrocarbon? If you have watched the lecture, then you must know. No? Okay, so we'll discuss this. So first one is carbon films with higher density and higher La by Lc value yield pyrographite. Okay, so which of the carbon film will yield pyrographite? Okay, so firstly I asked that in the question it was asking that how the HOPG is different from the pyrographite. So pyrographite will yield only when the carbon film will have a higher density. Okay, the term which is higher density, and the La by Lc. Hope you have remembered in the last class we have I have introduced this term what is La and Lc. So if you have not, if you do not remember, then please do watch my last interaction session. So here higher La by Lc, then it will yield a pyrographite. Pyrographite is heat treated to produce industrial grade pyrolytic graphite. Got it? So here it is saying the pyrographite is heat treated. We have to do some heat treatment in order to produce the industrial graphite. Okay, so which is nothing but the pyrolytic graphite. So there is a term pyrographite and pyrolytic graphite. So industrial grade is pyrolytic graphite and this is simple pyrographite. So in heat treatment can be performed by simple annealing or by hot pressing. So first term is here annealing. Okay, so so what is annealing? Firstly, you should know that what is annealing. Annealing is nothing but to exposing your material at certain higher temperature. Okay, so here it is related to the thermal treatment of the material. Okay, so if you are from the metallurgical background, then you must know this term. What is annealing? What is normalizing? What is quenching? So this is very helpful. So annealing is nothing but the you have to heat and you have to cool it down very slowly. So for the material processing here the it is one of the type of the heat treatment. So here can be performed by simple annealing method or hot pressing. So hot pressing, here you can see this is at certain higher temperature, higher temperature. Okay, and this is your material. Okay, so here we are pressing this material. Since this is at high temperature, the T is high, and we are applying some force press. Okay, so this is hot pressing, and here you can see the structure is like this, zigzag zigzag. So after pressing it will become like this, somewhere around this flatty, not like a zigzag. Okay, so pyrolytic graphite is called highly oriented. So this pyrolytic graphite called highly oriented pyrolytic graphite if its mosaic spread angle is less than 1. Okay, so after pressing this pyrolytic graphite, So here this is highly oriented. Even in the order of the alignment is, I mean, it should be very aligned such that the angle between this two should be less than 1. So here you can see this is alignment. So here this angle should be the less than 1 degree. So that's why it is called the highly oriented, means there is no misorientation in the pyrolytic graphite. So that's why it is called a highly oriented pyrolytic graphite. So here the new term came, which is Mosaic spread angle. So this is about this angle. Okay, which angle? This less than 1 degree. So what is this? The spread of polycrystalline graphite tiles should be so flat that two adjacent tiles never have misalignment, and it should be less than 1 degree. So there is, suppose these are the tiles of your pyrocrystalline graphite. Okay. So suppose this is one tiles. Okay. And there will be another tiles. Sorry. Okay. So this alignment, or suppose there will be another more. So the angle which will come here between these two, it should be less than 1 degree. Okay. So that's why this angle is called mosaic spread angle, and the spread of polycrystalline graphite tile should be so, such alignment should be such that it should be the misalignment should be less than 1 degree. And HOPG is polycrystalline similar to mica. It can be exfoliated to produce single graphite layers. So the next question came is that application. It is very important that where we can use this. If we have any material, if we know the property of that material, then we should know that how can we use that material. So here in the diagram, sorry, in this figure, you can see the commercially, which is commercially available HOPG. So how it is mainly look like. Okay. So first thing is crystal optics. X-ray diagnostic tools and spectrometer. We can use this. Second one is ion beam detectors. We can use this in ion beam in order to detect any beam, ion beam. Third one is as a electrode or the conductive support. Since this is a carbon material, since that's why it has some conductivity. I do not have the exact that how much. I mean its conductivity in which range. But yeah, since it is conductive, we can use this as a electrode material. Fourth one is test sample for the various instruments we can also use. Other method here, graphite precipitation from carbide, which is you can say any metal or silicon carbide. Okay. So again we will come in the question that HOPG is different from the pyrographite is how it is highly aligned crystal. Okay, we got here now the angle mosaic spread angle is very less. So that's why it is highly aligned. So the answer is second one, highly aligned crystals. Clear? Any doubt? No? So let's move to the another question. So another question is change in the enthalpy of formation of hydrocarbon gas from negative to positive at a certain temperature indicates that it becomes more stable compared to the other hydrocarbons. It cannot used as a precursor for graphite. It is thermodynamically favorable to obtain it during pyrolysis of a polymer. It is thermodynamically favorable for it to dissociate. So first term here it came is the change in enthalpy. Okay, so you should know that what is change in enthalpy of formation of hydrocarbon. Okay, so here it is asking mainly from the negative to this is having some problem. Negative to positive at certain temperature indicates what? So here when your change in enthalpy of form when we form some when you when there is a formation of hydrocarbon gas, then it is going from the negative to positive. Okay, so what it will indicates, the question is asking this. So you should know when the change in enthalpy is going from the negative to the positive, then what is its indication, and when any reaction is giving change in enthalpy from positive to negative, then what is indicating. So you should be very clear between these two, at what it exactly uh, telling you or indicating. Okay, so can you guess what it could be? Okay, so I will discuss this. Okay, so here in this uh, pyrolysis, we have to know that what is pyrolysis? The thermomechanical decomposition of a solid, liquid, or gaseous phase hydrocarbon in absence of the oxygen. So here there is no oxygen gas is present. So we have to do the thermal. I mean, either it could be in the presence of like your an inert gas or the vacuum. So it is a thermomechanical. Okay, so here thermomechanical it means what? Here your temperature is also involved plus pressure, any kind of a. So and you will decompose the solid, liquid, or gaseous hydrocarbon. Okay, and the oxygen should not be present. So here since this is for the solid state pyrolysis, here we are using some solids in order to decompose the hydrocarbon. So as a solid, what we can take is the thermosetting resins. We can take some petroleum cokes, and if in case of the liquid phase pyrolysis, we can use the petroleum pitches or any polymers which is in the liquid or the liquidase form. And gas phase, we can use any light hydrocarbons such as methane gas or acetylene. So here the all forms of pyrolysis are used for carbon manufacturing, various graphitizing or non-graphitizing carbon as well as crystalline graphite. So first question is that what happens during the pyrolysis? Second is, so what happens is that firstly, so here we are decomposing the hydrocarbon. Okay, so hydrocarbon, you know now, where the hydrogen and carbon both are removed. So suppose this is like your hydrocarbon, if you will, if you know this all. Okay, so hydrocarbons are broken into small molecules. The first one is your broken, sorry. Okay, the second one is non-carbon atoms are released after cleaving from the parent atom. So whatever, suppose sorry, suppose you have this CH4, then the non-carbon atom, suppose this here is a hydrogen, so it will get removed. Then the third one is some cyclic carbon structure are formed. So any cyclic kind of a structure, you can say any, this will be formed. And then the combination of your one and third. So one is what? Hydrocarbons. Again it will break. And third is what? Again cyclic carbon structure will form. So here the formation is happening, dissociation, or so here you can see in some cases formation of the compound, and in another cases dissociation of compounds is happening. So it depends on what, I mean, how you will determine that whether it will be a formation or the dissociation. So it is depends upon the enthalpy of formation. So what is the enthalpy of formation? Here is the definition. Okay. Yeah. So what is this? So change in enthalpy for getting 1 mole compound from its element. So what is the changing enthalpy is happening for getting 1 mole compound from its element is nothing but the enthalpy of formation and stability at given temperature. So we require negative enthalpy for the compound formation, right? So if the formation is happening, then the change in enthalpy will be negative, and when there will be a decomposition, then it will be a positive change in enthalpy. Okay, so for example, formation of methane in a polymer pyrolysis will occur if methane is very stable at given temperature. On the other hand, pyrolysis of methane itself will take place if it is not stable at a given temperature. Okay, so here the main thing is this formation, or here you can see the compound formation and compound dissociation. Okay, so here it is asking that change in enthalpy of formation. Okay, so there is a formation is happening, and the gas from the negative to positive certain indicates what? It become more stable compared to other hydrocarbon. It cannot be used as a precursor for graphite. It is thermodynamically favored to obtain during pyrolysis of a polymer. It is thermodynamically favorable for it to dissociate. So it will be mainly for the dissociate, because here it is going from the negative to the positive. Okay, so since it is going from the negative to the positive, so it is more prone to dissociate, right? So it is making thermodynamically favorable for it to dissociate, since it is going from the negative to the positive. If it will goes from it goes from the positive to negative, then it is thermodynamically favorable for the formation. Clear? If you have any doubt, then you can put in the comment box. So the next question is, Kish graphite is formed when the temperature pressure is below the liquidus line of the phase diagram, above the liquidus line of the phase diagram, below the solidus line of on the phase diagram, or above the solidus line in the phase diagram. So if you know this, sorry. So if you know that this, sorry, phase diagram. So in the last lecture, I have shown you the phase diagram for this carbon, and there also I have introduced that what is liquidus line and what is solidus line. Okay, so if not, then you can watch the last lecture, or you can use any physical metallurgy book or any introduction to material science. You can use this book, Introduction Material Science, or any physical metallurgy book. So there you can find easily that what is phase diagram, or how what is the reason behind forming this phase diagram, what it gives, what is the advantage, what is the solidus line, liquidus line, and what kind of phases form when you go above or below from the various liquidus or the solidus point line. So this is all about. So in this question you can see, so it is asking about the Kish graphite. Okay, so Kish graphite is what? Firstly, precipitates during the steel manufacturing on melted iron surface. Okay, along with the other residues. So when there will be the steel manufacturing will be happening on the melted iron surface, so Kish graphite will precipitate. It is refined using sieving, floating, milling, magnetic separation. So this all the this kind of a process, separation or the beneficiation process I have discussed in the last lecture. So up to 99% purity and scale of the flags we can achieve from this process. So it grow as dendrites which form plates. Okay. So here you can see it grows as a dendrite. So this is like this dendrites you can see here. Okay. So and it span up to several centimeters, and its thickness varies from 0.01 to zero point 0.1 mm. So it is quite big in size, and fast cooled Kish graphite has thinner plates. Okay, so if you will do a fast cooling, then the plate size will be thinner, and but longer dendrites. Okay, so the thickness will reduce, but it will be a longer in the size. Slow cooled, if you will do a slow cooling, then it has a thicker plate. It will be a thick, and the size or the length will be the smaller, the less plate. So they exist in the form of small platelets that are powdered or directly used in various applications. So here, mechanism of formation of the Kish graphite is what? When carbon iron alloy. Okay, so if you know the carbon iron phase diagram, then you will know that how carbon iron alloy will form. So it will melt. So there will be a melt of the carbon iron alloy, and it cooled below the liquidus line. Below the liquidus temperature, carbon started to precipitate, or the carbon precipitates as a graphite below the liquidus line. And this is atomic deposition of carbon okay, will be happening. So here it is the deposition. How this deposition will take place? It will be a layer by layer under the sudden change in the temperature, okay, because we are cooling going from the higher temperature to the below the liquidus line or below the liquidus temperature. So temperature, and in this way the graphite is started to form. So this is how the formation of this case graphite will happen. So the growth mechanism, suppose, okay, so it started to find. So in any nucleation and growth, when you will see it started forming, but it also needs the growth, okay. Nucleate after nucleation, it requires the growth, okay. So it involves nucleation, growth, and so firstly from anyway it will start to nucleate, then it will grow, and that will then it will spread all around to form a bigger crystal in a more rapid manner. Now, this graphite is usually directly and after pulverization in batteries and related application, we can use this kind of a graphite. And this is similar to natural flake graphite, but industrially the term Kg is more common. So we also call this natural flake graphite. So here you can see this is like a flaky kind of a structure here. So firstly it starts to nucleate, then it starts to grow, and after growing it forms a big size of this. You can see a very bigger crystal, and it is oriented like this. Okay, so it is, so inside if you will see in a optical imaging like SCM or TM, it will be a mainly like this flaky kind of a structure. So it is also called a natural flake graphite, but in more industrial term it is like a KG or the fish graphite, right? So liquidus line, so you should know that again the liquidus line is the equilibrium phase in the phase diagram, and is this line between the liquid and liquid plus solid phase. Okay, so firstly it will not directly convert. Whenever you see the phase diagram, the liquid does not convert directly from the liquid to the solid, then there will be a in between liquid plus solid phase. Okay, so the liquidus line is what, where your transition will happen from the liquid to the liquid plus solid phase. So liquidus line is equilibrium phase where in the diagram, and that is between the liquid and the liquid plus solid phase. Okay, so here your kiss graphite formation starts to begin. So in this option what we had is like that: the temperature pressure below the liquidus line on the phase diagram, above the liquidus line. So here it is below the liquidus line. Okay, so below the temperature pressure is below the liquidus line, our kiss graphite starts to form. Okay, I hope this is understand, and if not, then please do check that how I mean the phase diagram which we have discussed in the last class. You can see that where the liquidus and the solidus and how it is converting and where it can form. So it will be a more helpful for you guys to understanding a better. Okay, okay. Now the next question is, if polymer feature a high carbon content, it will always yield graphite, always yield glass. Like suppose if it is asking polymer features, if any polymer is having a high carbon content, then will it always yield graphite or the glass like carbon, or either graphitizing or non-graphitizing carbon. You should know that what is graphitizing, what is non-graphitizing carbon, and never yield non-graphitizing carbon. So can anybody guess what it could be? Okay, So here the two term came, which is a graphitizing carbon and non-graphitizing carbon. So what is this? Okay, so let me show you this slide. So in this you can have a better classification of polymer derived carbon. Okay, so in the polymer also this is like a hydrocarbon. Here you can also form see some carbon. So here this is polymer. So there is a two process. So HC is what? Hydrocarbon, and HOPG is what? Highly oriented pyrolytic graphite, as we discussed in our earlier slide. So HC pyrolysis, it means hydrocarbon when we do the pyrolysis. Okay, where pyrolysis, you know that how uh, it happens, as we discussed in our previous slides. And then polymer. So in polymer we obtain two process. This we will discuss in our later slides, that how it happens, this coking and charring. So polymer is what here, when you do this coking, then you will form a pyrolytic graphite, cokes, glass-like carbons, activated carbon, low purity jars. And this charring is what you will form, sorry, in coking, coke, glass-like carbon, pyrolytic carbon, and in this charring you will form a activated carbon and low purity jars. So this is graphitizing, where you are forming pyrolytic graphite from your HC pyrolysis and the coking of the polymer. And this is your non-graphitizing. Non-graphitizing is what? Where cokes, glass-like carbon, activated low purity carbon. Okay. So the non-graphitizing carbon are those which cannot be converted into graphite. So this is even when heated, even when you heat. So suppose uh, non-graphitizing carbon is what? It cannot convert into graphite even though if you apply a very high temperature. Okay. So even at higher temperature also, it cannot convert into graphite. Okay. So this is what? Non-graphitizing carbon. Okay. Now they have complex structure formed by the curved carbon hydrocarbon sheets during pyrolysis itself. Such structures have curls, folds, and spherical units which cannot open and become graphene sheet. Glass-like carbon and activated carbon are non-graphitizing carbon. Okay, so glass-like carbon, activated carbon are what? Non-graphitizing carbon, and with very different property. Okay, and here in the opposite, I have introduced the non-graphitizing carbon. But what is graphitizing carbon is what? It is opposite. So how it will opposite? It can convert into the graphite. Okay, so this is what? Graphitizing carbon. Okay, so here in this question, the polymer feature a high carbon content. It will, I mean, sometimes, so that's why it can yield either a graphitizing or non-graphitizing carbon. Okay, it is not like that it will always yield a graphite. It is not sure like this, and it is not like always yield a glass like carbon, or the always it is, sometimes it is graphitizing. It means that can be converted into the graphite, and sometimes it cannot convert into the graphite. So both it will yield either a graphitizing or the non-graphitizing carbon. Hope this is clear or not, then you can comment in the comment box, and uh, in the YouTube also. So where I can, there also I can answer your questions, that if you will have any doubt related to any slides. Okay. So again, okay, so the one which I discussed in the just before slides, the question came here. What is graphitizing carbon? Okay, so it is something related to graphite. So the graphitizing carbon is what? Which converts into the graphite. And I explained like what is non-graphitizing carbon, which is what cannot convert into graphite. But here graphitizing carbon is what? It can convert into the graphite. So here in the option we have a type of synthetic graphite, a carbon that can be converted into the graphite. So yes, this is that. And highly graphitic carbon, polymer that can be converted into carbon. So a carbon that can be converted into graphite is what? Graphitizing carbon. So here also you can see that what is graphitizing and non-graphitizing carbon. So if a carbon material does not obtain a 3D structure, even at 3D crystal structure, even at 3000 degree centigrade, okay, that's mean even if you will go at a very high temperature, more than the 3000 degree centigrade, then also it will not obtain a crystal structure. Okay, so it is called a non-graphitizing. These materials do have a short range order, but in addition to flat graphene sheets, they also contain curved carbons. Okay, and mainly crystallinity measurement techniques for graphitic carbons are X-ray diffraction, TEM, Raman spectroscopy. So from this we can do the characterization of this graphitic carbon. And here in this you can see how the graphite looks. So this is for your graphite. This is for your graphitizing carbon, and this is your non-graphitizing carbon. So you can see that it is not like a crystal structure, no any crystal structure, no crystal structure. But here you can see clearly a crystal. It is high. Orientation is also good. So crystal structure here you can see, but here it is not forming any crystal structure even at a high temperature. Here it is alignment is also good and it is forming a crystal structure here. Okay, so this is all about this. So graphitizing carbon is what? That carbon can be converted into graphite. I hope this is clear. So let's move to the next question. So the next question is what? A difference between coking and charring is what? So coking is a property of natural polymers, while charring is a happens in synthetic polymer. Coking yields graphitizing carbon, while charring yields non-graphitizing carbon. Coking yields black carbon, while charring yields brown carbon. Coking yields carbon with flat surface, while charring yields porous carbon. So this we will discuss. So first thing here, the two term came is first one is coking and sorry. What is this? What is coking and what is charring? Anybody knows this? What is this? So it is asking what is the difference. So in this slides, I will tell you about this again, this polymer derived carbon. So here you can see in the polymer derived carbon, the pyrolysis of polymer does not always yield graphite. Okay, so when you will do the pyrolysis, it is not always necessary that it will yield a graphite. It is not always be like that. So there are two primary mechanism of carbonizations of polymer. Okay, so when you will do the carbonization, there is two mechanism. One is coking, another is carrying. So what is coking? Hello, 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 hello. Khush, are you able to hear me? Hello, hello. Am I audible? Hello. Okay, yeah. So, anyways, let's just see. So, the cooking. So, during its carbonization, the polymer passes through a liquid or semi-solid state at least one. Okay. So, in this case, your polymer needs to pass through a liquid or semi-solid state at least once. At least once. Okay. But in carrying, you can see here, if during the carbonization the polymer remains rigid and does not pass through any liquid state. Okay, so here your polymer during the carbonization, it does not pass through any liquid state even at once. Okay, so here the polymer structure will what happen? It will remain like a skeleton or the rigid. So this mechanism is called carrying, and this is what coking. So suppose if you will have any polymer cube, you will have a polymer cube, and if you do a coking mechanism, here you can see one or two. So here it is passed through a liquid or semi-solid state at least once. So here you can see this kind of a structure you will get, but here because it is like not pass through any liquid state, so what will happen here, it will remain rigid and skeleton will be the remain here. So that's why you will find some porous kind of a structure. Okay, in carrying. So here you can see these all are what. So this is what porous. So here also you can see this kind of a porosity you will generate in carrying. Okay, so illustration showing shrinkage on carbonization of a polymer structure. So this is the possible carbon structure after heat treatment pyrolysis. So this So here it will be a more like this kind of a structure you will form after the coking, but here it will become a porous. So combination of both mechanism is also possible. In both cases there is a net mass loss from material which leads to shrinkage, coking, or porosity carrying. Okay, so there will be a net mass will be happening of the material from the material which leads to shrinkage. So because there is a reduction in the mass, so that's why some porosity will be formed in case of carrying, or there will be the shrinkage in case of what, coking. So coking carbons are dense, and this cares carbons are what, porous. So this is what here you can see that it is more dense, but here it is porous. So this is the difference. So the question is asking the difference between coking and carrying is what? So here coking yields carbon with a flat surface, while carrying yields carbon with a porous surface, or you can say the porous carbon. Okay. So this is the answer. I hope I have explained it. So let's move to the next question. So the next question is asking about which of the following carbon is obtained when polymer undergoes carrying during the heat treatment. Okay, so this is very clear. Just I have explained two terms. So when the first one is coking, and the next is carrying. So it is asking about here what you will get here. Okay, so this is mainly asking this. So you will get a high oriented pyrolytic graphite, or the glass like carbon, or the porous carbon, or the pyrographite. So just in the last slide I have explained, and again in the same slide I will explaining this same thing. So here this is your polymer Q, and this is your carrying, and this 3 and 4 is the result of the what you are carrying. So here as you can see that this is what? This is nothing but the pores. Sorry, this is pores. So here also you can see some pores you will find. So in carrying here, as you can see, in both cases net mass of because there is a material loss, so that's why there will be a, in case of coking there will be the shrinkage, and in case of the carrying there will be the porosity. Okay, so the coked carbon are mostly dense, and this is pores. So here it is, you can see more like a dense structure, and here it is more like a pores structure, like this. Okay, so again the same slide, I will not spend so much time in this. So it is what, in the polymer ion carrying heat treatment, it will give a porous carbon. Fine. Okay, so the next question is thermal cracking of gaseous hydrocarbon followed by pyrolytic graphite deposition is also known as what? Calcination, combustion, CVD, carbonization. So I have explained you in our previous lectures what is calcination, what is combustion, what is carbonization. So I think the new term came here. It is not very new. If you know that chemical vapor deposition, if you have been through any courses, chemical vapor deposition, and in short, it is called CVD. So if you know, there is like many techniques for the thin film deposition where we will do CVD, PVD. PVD is what? So here it is chemical, here it is physical. Okay, like sputtering and all. So there are a lot of techniques. If you will see any books related to thin film growth, there you will find this kind of a techniques. So thermal cracking of gaseous hydrocarbon, so here the term came thermal cracking followed by pyrolytic graphitic deposition is also known as what? So we will see that in this slide. So here you can see in the pyrolysis, the pyrolysis is a thermomechanical decomposition of organic material in the absence of oxygen that I already explained. So the decomposition of the hydrocarbon must be thermal. Okay, thermal it means only you have to apply the temperature. That is, other chemical reactions such as oxidation should not be included in that when you will do the decomposition. Pyrolysis is not limited to polymers. Any organic materials can be pyrolyzed. Okay, so here you are applying just a thermal, so you did not to restrict yourself just to you only allow the polymer material for the pyrolysis. Can be any organic materials too. So the polymers always yield some solid carbon, right? Sorry, pyrolysis always yields some solid carbon because there will be some carbon, obviously, but depending upon the pyrolysis condition and precursor, the fraction and purity of pyrolytic carbon may vary. Okay, so what is the I mean, it depends on the various factors like what are the precursors you are using, some temperature, pressure. I mean, you have to maintain all the conditions in order to get the what is the purity of your carbon that you are getting in your pyrolytic carbon. Okay, so there are many factors which will affect the purity of your carbon. So here the gaseous carbon can also be pyrolyzed. In this case, the process is also called cracking. Okay, so the gaseous, suppose let's say the methane you are doing for the methane require a relatively high temperature, so around 1200 degrees centigrade, and the catalytic support where carbon can be deposited. Okay, so a refined version of this process is called CVD, chemical vapor deposition, which is used for making carbon nanomaterials such as graphene or carbon nanotubes. So here what is happening? So so suppose this is a CVD, this will be you have to know that how this CVD is happening. So for the more details, you can watch any lectures, or here also in the lectures you can see thoroughly. But here I will give you a very brief. So here Suppose this is your heated substrate, and there will be the atom A, and this atom A will come and hit atom B. Okay, so there will be the generation of the C, and then this will be in the presence of the catalyst or other environment chamber. This will give you the, and here the catalyst is coming. Okay, so here mainly the heated substrate is also used in this case. But here, like as I said, that for this process, for the detail, you can watch the lectures. I will just giving you a brief. Similarly, here it is happening in the presence of the catalyst here in this chemical, and similarly in the PVD also, some atoms, suppose here you have a target metal, so then some atoms comes and hit the atoms of your target material, then it will go and deposit it on your substrate here. So it will started to deposit it like this. So this is mainly in the PVD, but here it is mainly talking about the CVD. So since here we are using your catalyst. Okay, so here thermal cracking. So here, like I just explained, the term called cracking gas can be pilot. In case of process is also called cracking. So the thermal cracking of gases followed by polytic is also known as what? CVD. This is called the CVD, which is nothing but the chemical vapor deposition. Okay, so let's move to the next question. Which of the following takes place during the pyrolysis of the polymer? So again, the same, I think these questions are, I mean, we are getting again and again. So polymer chains align form graphite crystals. The d-spacing between the carbon sheets is reduced. Various hydrocarbon radicals are generated. Polymers molecules break into volatile, non-volatile hydrocarbon. So what could be the answer? It is more than one could be the correct. So let's see here the pyrolysis. The inert heat treatment of polymers consists of the following steps. The first one is your removal of water, solvent, or the volatile impurities. Okay, so this will, sorry. So up to 200 to 250, what will happen? The removal of water or solvent, and if there will be any volatile impurity will be happen, then it initially till 250. Okay, your all the water content will get removed. Then the cleavage of CO or CX. So 250 to 350 degrees centigrade, your all the present cleavage of CO or this C single bond any hydrocarbon that will be volatile till 350 centigrade. After that, if there will be the any CN, then till 500 degree it will remove. Okay. Then CH bond will remove till 700. Then the formation of your CC bond will occur at how much? Till 700 to 2000. Then increase in La and Lc up to 3000 degrees centigrade. Okay, so these are the inert heat treatment of polymer consist of the following steps. Okay, so this comprises of total 6 steps. The removal, there will be the removal of your water or any volatile impurities, then COC and CH bond, and then there will be the formation of your CC bond till 2000, and at very high temperature the La and Lc will increase up to 3000 temperature. So this process is mainly called where your formation of your CC bond is happening. Okay, so this is called carbonization, and okay, and where the La and Lc is increasing, which is called graphitization. Graphitization. Since the first step of the process is pyrolysis, often entire heat treatment is called pyrolysis. Okay, because the first step is process is pyrolysis. So the exact temperature value for different segments can vary depending upon the precursors that we are using, heating rate or the ramp rate, that what in what speed that we are increasing our rate, at what degree centigrade per minute or per second we are applying, and the environment which we are using also influence that environment. That's it mean what are the I mean the present gases, or if there is some inert gases is present, so that also influence the polymer pyrolysis chemistry. And during the pyrolysis of the polymer, multiple reactions take place and several radicals will form. Some dissociation of will happen, and that will again reformation will happen. Okay, so and some new hydrocarbon and carbon fragments will generate, and in micro and nano structure, many I mean graphitized temperature as low as 900 degree centigrade. Okay, so here you can see that so during the pyrolysis of the polymer, so what is happening here? What is happening? So you can see the various hydrocarbon radicals are generated that we saw here, and polymers molecules break into volatile and non-volatile hydrocarbons. So The answer is your various hydrocarbon radicals are generated and polymer molecules break into volatile and non-volatile hydrocarbons, that is at around 250 degrees centigrade, and the radicals are forming. Okay, so this is mainly the pyrolysis of a polymer. So the answer is this last two. So the next question is, all polymers undergo pyrolysis between 300 to 600 degrees centigrade. So all polymers undergo, I don't think so, the pyrolysis, all polymers will go under this fixed temperature. So it is not very true. So here you can see here the pyrolysis, some polymers can, it depends on the, I mean, as here you can see the exact temperature, different segments, so the precursors and what are the heating rate and what are the environment we are using. So it can go, not restricted to the 300 to 600, sorry, 300 to 600, it is not like that. You can here see that the range of the temperature, so at different temperature or different phenomena is happening. So even at a very high temperature also, uh, at very high temperature also, your pyrolysis will happen. So it depends on the precursor you are using and the heating rate, ramp rate, environment conditions and all. So it is false. Okay, all hydrocarbons yield some fraction of carbon on heat treatment. So here again the same thing, the slides which came. So here you can see the hydrocarbon. Okay, so it obviously, when you will do some heat treatment, then because it is hydrocarbon, then when you will do the heat treatment, then it will give some. Why? Because here you can see firstly why it is happening, because in this heat treatment process, suppose let's say you will take a pyrolysis, then your hydrocarbon, so okay, so it will firstly small molecules, it will make small molecules, okay, and then non carbon atoms, suppose non carbon atoms like hydrogen, that will be removed, okay, then your some cyclic carbon structure will form, and then the combination of 1 and 2. So here, that's why the some only the non carbon atoms are removed, but the carbon will, some amount of carbon content will still remain, okay. So that's why even after a heat treatment of your hydrocarbon, there will be, when you will do any heat treatment, then some carbon content will be there. Got it? So it is true. Now, the uh, carrying polymer doesn't pass through a semi-solid phase during its carbonization. So as I explained here in this slide, so the in the coking only you will pass through a liquid or semi-solid state at least once, but here does not pass through any liquid state. So that's why here you will get some porous kind of a structure because it is not passing through that, and here you will get a rigid or a more dense kind of a structure. Here you can see, here you can see, okay. So the coke carbons are dense and this is porous, so it is true. True, why? Because it does not I mean, you can say here, because in the coking because here you can see in the coking, polymer passes through liquid or semi solid, okay, either liquid or semi solid, but in carrying, in case of this, it does not pass, sorry, does not pass through semi solid or the liquid, okay. So it is true. Yeah. So the next question is, in X-ray diffractogram of um, non-graphitizing carbon, all peaks are sharp. Okay, so is it a true or false? So here, if a carbon material does not obtain a 3D crystal structure, so it is mainly asking about the non-graphitizing carbon. So non-graphitizing carbon is what? That will not convert into the graphite. Okay, so even at a very high temperature, let's say at 3000 degrees centigrade, even it more so that is called a non-graphitizing carbon. So these materials do have a short range order, but in addition to flat graphite sheets, they also contain curved carbon. Main crystallinity measurement techniques for graphitic carbon are X-ray diffraction. So here, how you will measure the main crystallinity? So by using, you can use XRD, TEM. Also, you can use Raman spectroscopy. Okay, or here also you can XRD in XRD crystallinity is determined by measuring the diffraction angle. Okay, which indicates the bond length. Sharp peak implies most bonds are of the same length. Okay, so here if we will know the XRD, okay, so XRD is mainly when you will see the plot of the XRD, you will find some intensity versus 2 theta. Okay, so it also, if you learn for in XRD, you should know that n lambda equals to 2d sine theta. Here it will be equal, so it follows the Bragg's law. So here this will be the 2 theta. So in the XRD, what it gives, it will show when there will be your peak or something like comes, then what does that mean? It is a crystalline in nature. Okay, and when suppose your material is amorphous, then it will give something like a hum kind of a structure like this. Okay, so this is what? Not crystal, it is amorphous. Okay, so in the XRT you can determine that whether your this material is a crystalline or not. So determined by measuring the diffraction angle of X-ray, so which is nothing but your theta or 2 theta, which indicates bond length. Sharp peak implies most bonds. Okay, so if you will get suppose a very sharp peak, suppose you are getting like a small peak and like this sharp peak like this, then it shows the bonds are of same length. So non-graphitizing carbons feature a range of bond lengths. Okay, hence a hump or the broad peak will occur. Okay, so here you can see because it is not a crystal, you will not get this. I mean, you will get like I said, this is not a crystal, so that's why you will get this broader peak. You will not get a very sharp peak. So here also, since this is a graphitizing carbon, here this is a crystal, you will get a peak like this. And since graphite here also you can see it is very good orientation. So here also it will give a good peak of your in the XRD. So what was the non-carbon? All peaks are sharp. So it is false. Why? Because it will give you a broader peak or a hump kind of a structure or peak. Clear? Because obviously this is not a crystal. Even you will get a higher temperature, then that's why it is called a non-graphitizing. It will not come converting into the graphite, so it will not obtain any crystal structure. So again, the same question related came. Non-graphitizing carbons are exhibit a short range order, hence they can they can be converted into graphite at heat treatment. So no, it cannot convert. Just I explained. So that's why it is false. Okay. So it cannot, even though if you will go more than the 3000 degrees centigrade, it cannot convert into the uh, crystals in or into the graphite. That's why it is giving this kind of a structure when you will do some XRD. This is so it will say not crystal, does not give sharp peak. Okay, so this is the that. So it is false. Okay, so let's talk about something called the graphitization. What is graphitization? So firstly, what is graphitization is that conversion of a carbon having layer plane structure with near parallel stacking into hexagonal graphite crystallite. So that is called the graphitization. So here in this, the last step of heat treatment, precursor has already converted into carbon. Okay, whatever the precursor, so that will convert into the carbon till the last step. So the precursor are typically needle cokes. You can take pyrolytic carbon from gaseous hydrocarbons. You can take graphitizing carbon. You can take as a precursor obtained from the solid phase pyrolysis. Graphitization is a kinetic process. If a graphitizing carbon is kept at certain temperature for a very long time, its sheets will align. Okay, so what it is saying that, okay, so it is saying that when the graphitization is a kinetic, if a graphitizing carbon is kept at a certain temperature, okay, let's say suppose at certain let's say T temperature, it will keep for very long time, then it will align automatically. Okay, and for kinetic measurement, we require information about each reaction, formation of intermediate products throughout a reaction. This is not possible for graphitization since the graphitic crystallites are not forming from another crystal. It is a process of defect annealing. So here graphitizing of carbon, here you can see, I mean, as you can see here, it is not aligned here in this case, and not aligned. But here after keeping at certain temperature, it will become aligned. So this is graphitization, graphitizing carbon. Okay, and if it is a non-graphitizing carbon, then it will not align. See, okay, so this is called a non-graphitizing carbon. So here in the question or in the assignments, you can see any question, the degree of the graphitization, which is denoted from the letter G, and it is given by the 3.44 minus D space 0.086. So you can get this for the your various temperature. So this 3.44 comes from the maximum D spacing you can obtain from the turbostatic carbons. So it is debated whether the maximum spacing for turbostatic carbons should be fixed to maximum of 3.44. The formula higher gives the normalized value, increase the D. So here you can see also for the graphitizing of carbon, let's say your D spacing is 3.42, then at certain temperature, then how you will get the graphitization. So suppose 3.42 and divided by, you can see, 0.086. So what you will get here? So when you will do calculation, you will find some 0.23256 something. So this will be your degree of graphitization. Okay, so G ka value, so the value of G you can find here. So in this way your numerical question can also you can solve if you will have any question in your assignments. This is very simple formula. Now the graphitization of cokes. So when you will do the graphitization of the coke, so one can measure the graphitization in the following ways. So by measuring the value of D spacing, so using XRD, you can, XRD you can have some you will get a peak, and from there, if you will know the XRD analysis, then from there you can analysis the D spacing. And by measuring the properties of the intermediate material, so let's say some properties like electrical properties, some you can say the resistance or the conductivity of the material, or the sheet resistance, and the magnetoresistance also you can. So you can the intermediate material will be there, and you can measure the property of those materials, and by that also you can measure the graphitization. So the graphite has a high thermal expansion along the C-axis during heat treatment. The first D first decreases and then it will increase. So in the case of solid liquid state heat treatment, graphitization take place more than 1000 degree centigrade. Mechanism of graphitization of hydrocarbon deposited carbon slightly differ. So industrially the term coke is used for the synthetic polymers. So let's say suppose PVC, polyvinyl chloride, and heated up to 1000 degree centigrade. So this is the graphitization of the coke. Okay, so here you can see unit cell height, and when you will do the heat treatment, it is in the minute. So you can the unit cell height. Okay, so when you will suppose at 12 you are doing it 2200, then the heat treatment time, when you will increase, then the unit cell height will start to decrease. So here this is the graphitization of the petroleum coke. Okay, so that's why it is saying the graphite has a high thermal expansion along C-axis. So during the heat treatment, the D first decreases and then increases. Okay, so here you can see the unit cell height is starts to decrease first, but here it is decreasing. And graphitization of cokes can be divided into two regions. Below 800 degree centigrade you will get the increase in La, and above 2200 degree centigrade, okay, so let's say Here if you will go above 200, so there will be decrease in the LC, decrease in the LC above 200 degree centigrade, sorry, 2000 degree centigrade, and there will be the increase in LA below 1800 degree centigrade. So here also there is a formula, the kinetic profile of the graphitization petroleum coke. It is given by the d dash d infinite plus d naught minus d infinite and the summation of your w e to power kit. So where your this d dash is interlayer spacing at any given time that you can find from your XRD, and d naught and d infinite are the initial and the final um, interlayer spacing, and W is your weight factor, K is rate constant, and T is your total heat treatment time that you are giving at particular temperature. So these are the parameters, and from that you can find the kinetic profile of your graphitization. Uh, so let's quickly discuss this, and then we will be closing the today's session, interaction session. And if you will have any doubt from this session after watching this video, you can ask in the next class. We'll be discuss all your problems that you will be facing related to these all topics. Okay, so let's quickly do this. So pyrographite or the pyrocarbon is what? The single or few layer graphite graphene flakes prepared by pyrolysis of hydrocarbon, and that can be hot pressed or annealed more than the. So here in the hot pressing also you can you will require a temperature more than the 2200 degree centigrade in a furnace for graphitization. The sheets are turbostatic, but they do not contain curved or completely spherical carbon. Okay, so that will be slightly like a wavy structure and but may disappear after the heat treatment. So average D spacing in the case of methane, like in the last slide we discussed, it is like a 3.42. So heat treatment is generally performed more than 2400 degrees centigrade, and the graphitization is influenced by the following parameters. So the first one is diffusion of voids and vacancy through the layers. So when you will do some apply some heat or pyrolytic film will be there, then the plastic deformation in thick pyrographite film will be there. Then such deformation can also internationally induced for improved graphitization. Pressure increase the hydrostatic pressure favors the process. More the pressure you will apply, more the process will happen. And the catalyst, when you will use any catalyst, like metals from carbides with the matrix precipitate graphite carbon. So here you can use titanium, nickel, boron, molybdenum, tungsten, platinum. But same what some of the first metals to be used as catalyst. So here you can see this is your D spacing, and after that this is like a misalignment usually, and here you can see the alignment. Okay, after using this catalyst. So yeah, so if you want to read further, these are some reference book that are there in the slides. So you can refer these books and from there, if you will have any doubt, then you can clear more. But yeah, if you also you will have any doubt, you can post in the chat box or in the comment box in the video. But that we can discuss and we can take those questions later on. Okay. So I hope this is clear to you guys, whatever we have discussed today. So see you in the next class. Bye bye.